Hello, this is part H of the Chapter 7 lesson. In this part, we're going to get our last type of hypothesis test in Chapter 7, one that we call a test of independence. Now, in the last part of this lesson, we looked at ANOVA, which was a way of comparing population means from two or more independent populations. A test of independence is going to be somewhat similar, but instead of comparing population means, we're going to be comparing population proportions. So this test is actually going to be very similar to our two-proportion z-test that we saw a few sections ago. And so to illustrate this, let's look at this first example, example 717 from the textbook. And the question here we're going to ask is living arrangement related to exercise frequency? And so to try to answer this question, some researchers went out and they asked a whole bunch of students. They surveyed a total of 470 students, and they asked them two questions. Where do you live? Do you live in a dorm, on-campus apartment, off-campus, or at home? And then they asked, how much do you exercise? Do you have no regular exercise, sporadic, or regular exercise? And so we had a total of 90 students who live in a dorm, total of 180 who live on campus, 150 live off campus, and then 50 live at home. We had 255 that do not exercise regularly, 125 exercise sporadically, and then 90 regularly. We have 23 who live in a dorm and who do not regularly exercise. We have, for instance, 25 that live off campus and exercise sporadically, and so on and so forth. So this table here summarizes our results, and this table is what's called a contingency table. Now this scenario is something very similar that we looked at when we did the two proportion z-test, where we compared two populations. We had the population of students from last year and the population from this year. This is kind of somewhat similar, but here we've got four different populations of students characterized by where they live, and we're kind of comparing these four different populations. We're asking, is exercise habit related to where they live? Or state another way, is there a difference between these four different populations of students? But we're going to state things a little bit differently than using proportions. First, let's make a couple of observations. We have two different variables involved in this scenario. We have the living arrangement and the exercise frequency. Now, living arrangements are kind of what's shown in the rows of this table, so we're going to call that the row variable. And exercise frequency are shown in these columns, so we're going to call that the column variable. Remember that we have a variable is something that can change or be different from person to person. So living arrangement and exercise frequency, those are indeed variables. And so we're asking, is there a relationship between these two variables? Does the value of one variable affect the value of the other variable? So that's kind of another way of stating our question. Okay. So our claim or research hypothesis is that there is a relationship between those two variables. Kind of seems reasonable to assume that one does affect the other, and so that's going to be our claim. So kind of in more mathematical terms, the claim is that the variables are dependent. Now, a dependent is the opposite of independence. We talked about independence back in when we talked about probability. Independence means that there is no relationship between two variables or two characteristics. But here we think that there is a relationship, so the variables are dependent. Now, in all our other hypothesis tests, the first step was to define the parameters. In this type of hypothesis test, there really are no parameters. We could define parameters, but there'd be a whole bunch of them, and it'd be rather complicated. So we're not going to talk about the parameters. We're just going to talk about things in terms of dependence or independence. Okay. So now our hypotheses, we're not going to have any parameters in our hypotheses like our other hypothesis tests. As always, the null hypothesis is that there's no difference or no change. And so no difference in this scenario means that things are independent. So our null hypothesis is a statement that frequency and arrangement are independent. And the alternative is the same as our claim that they are dependent. Okay? An equivalent way of stating these hypotheses is the null is that frequency and arrangement are not related, and the alternative is that they are related. So not related versus they are related. And the type of test that we're going to do here is called the chi-squared test of independence. Earlier we saw the chi-squared goodness of fit test. The theory behind this test of independence is very similar to the goodness of fit test. The book gets a little bit into that, but as always we won't get into that here in this lesson. We're just going to go to the worksheet titled Independence, and we see a lot of green cells and a few yellow cells. Over here in these yellow cells we're going to enter our contingency table. That contingency table we'll call the observed frequencies, and we can set this up so that we can have as many as 6 column variables and 6 row variables. In this case we've got only 4 rows and 3 columns, so we enter our data here. All these totals are automatically calculated, and then the Excel calculates the expected values, these expected values are somewhat similar to the expected values in the chi-squared goodness of fit test. These are the frequencies that we would expect if the rows and columns were independent. And so for instance here, if things were independent in a sample of 470, we would expect there to be about 48 people in this first category but we actually observed 32. So we observed 32, we'd expect 48. There's a bit of a difference there. And likewise, we could compare these other expected values to the observed values. Now, down here, what we call the intermediate calculations are where we kind of measure the difference between these observed and expected values. The calculations here are very similar to the chi-squared goodness of fit. We take each observed minus the expected, square it, divide it by the expected value, and that's how we get this number here. And so to measure the total difference between the observed and expected values, we add up all of these intermediate calculations, and that gives us our test statistic. So this number here is a measure of the total difference between the observed and the expected numbers. And then based off of that, we calculate a p-value. As with the goodness of fit test, there is no left-tailed or right-tailed or two-tailed test. There's only this is always a right-tailed test, and our p-value here is very small, or 0. This calculates the degrees of freedom, and we could use that information to look up a critical value and compare the test statistic to that critical value as explained in the book. But we're just going to look at that p-value. We'll interpret that p-value like every other p-value. Compare that to the significance level of 0.05. P-value is much less than 0.05, and so our conclusion is to reject the null hypothesis in favor of the alternative. So we reject the statement of no difference or independence, and we favor the statement of dependence. So what that means in even less technical terms is that frequency and arrangement are related. So in other words, that we support the original claim that there is a relationship between exercise frequency and living arrangement. So the test that we did here again is called the chi-squared test of independence. The purpose is to test if the row variables of a contingency table are independent of the column variables. Now this test is one of the most frequent tests that you'll see in the journal readings, test of independence. And another way to state the purpose is that we're looking for a difference between 2 or more different populations. And so the requirements for this type of test are, number 1, that the data are represented as frequency counts and are randomly selected. This word here, frequency, is very important. Our data have to represent frequencies or counts. They can't represent measurements like weights or heights or distances or anything like that. And then the second requirement is that all the expected frequencies are at least 5. That's the same requirement as what we saw with the goodness of fit test. Our last example here is example 718 from the textbook. And in this example, we are comparing 3 different treatments for pain. And so what we do here is we give 50 patients a standard dose of a new pain reliever. We give another 50 patients a high dose of the same pain reliever. And then we give another 50 patients a standard pain reliever. And then we ask patients how much pain reduction do you have, and we categorize those results into 2 different categories, either meaningful reduction or no meaningful reduction. So we had a total of 64 patients with a meaningful reduction and 86 with no meaningful reduction. The numbers in the center say, for instance, that 23 of the patients taking the new pain reliever have a meaningful reduction. 39 of the patients taking the standard pain reliever had no meaningful reduction, so on and so forth. And so the question that we're asking here is there a difference in pain reduction between the 3 treatments? And so we've got our data here arranged in a table. Each number represents frequencies, and we're asking for, is there a relationship between the type of pain treatment and the amount of reduction. And so this is going to be a test of independence. Okay. So our hypotheses is that the row variables are independent of the column variables. So in this case, pain reduction and treatment are independent. The alternative is that they are dependent. Or equivalently, we could state these hypotheses is that there is no difference between the treatments and that there is a difference between the treatments. So again, we'll go to our worksheet independence. We'll enter our contingency table here, just as it was shown a couple of slides ago. Calculates the expected frequencies, the intermediates. Here's our test statistic. This case we have 2 degrees of freedom, and then here's our p-value. And so we interpret that p-value just like the previous example. It's much less than 0.05, and so our conclusion is to reject the null hypothesis. And so this means that in even informal terms is that there is a difference between the treatments. So all the treatments are not the same in terms of the meaningful reduction or not meaningful reduction. So they're different. Now, which one is different? Well, that would take a little bit more analysis. Like the ANOVA test, this test of independence doesn't tell us which population is different. It just tells us whether there is a difference between the population or not a difference. If we want to try to determine which one is different, that take a little more work, but we won't get into that here. Yep. So to kind of summarize all of Chapter 7, we've got we talked about a whole bunch of different types of hypothesis tests. And the calculations are all done in different ways, but they're all set up in very similar ways, and they're all kind of interpreted in similar ways. Kind of in general, is that in a hypothesis test we have 2 competing hypotheses. The alternative is that there is no change or difference between different populations, or from what we expect, or from what happened in the past, or whatever. And the alternative is that there is a change or difference. So the null hypothesis is no difference. The alternative is that there is a difference. In all of them, we calculated a p-value. If we have a small p-value, meaning less than 0.05, then we reject the null hypothesis, and our final conclusion is that there is a change or difference. If we have a large p-value, meaning greater than 0.05, we would not reject the null hypothesis and conclude that there is not a change or difference. So whenever we read a journal article and we see a small p-value, we can interpret that in general as meaning that there is not a difference between the 2 things that they're comparing, or the 2 or more things that they are comparing. If we see a large p-value, that means that there is no change or difference in the two or more things that they are comparing.